Welcome to OOTO TV, the out-of-the-office investigation from the past into the future of personal health and actualization. This time, we're discussing requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation. I'm Major, and with me is Lieutenant Colonel.
Okay, let's just jump right in. Lieutenant Colonel, I want you to picture this. You're standing right here, on the bridge of a ship that's longer than 3 football fields, carrying literally hundreds of millions of dollars worth of cargo? You're trying to navigate a channel that feels barely wider than the ship itself, and there are other massive vessels sliding by just meters away. I mean, talk about a high-stakes, high-pressure world. The technology you see all around you isn't just some nice-to-have gadget. It's the central nervous system keeping this whole massive operation from going disastrously wrong. We're talking about incredible precision, absolute safety, and a constant flood of data that needs to be interpreted correctly every single second.
You've absolutely nailed it, Major, and that really gets to the heart of what we're talking about today. See, this isn't just a story about cool tech. It's about a critical partnership, a dance between the human crew and their machines. So here's how we're going to lay it all out for you. First, we'll explore the modern bridge itself. Then, we'll get into the nitty-gritty, the core technical components. After that, we'll look at the absolute game-changer that was the GPS revolution. Then, and this is crucial, we'll talk about the indispensable human element. And finally, we're going to pull it all together to figure out how you define the requirements for the navigation tools of the future.
Right, so let's start with that modern bridge. You know, it's so easy to think of these systems as just a bigger, more expensive version of the GPS in your phone. But that could not be further from the truth. What we are really talking about is this deeply complex, integrated ecosystem of technology. It's a whole environment of radars, electronic chart plotters, depth sounders, speed logs, communications gear, all of it feeding this torrent of information to a central display. And the secret to making it all work isn't just having the latest and greatest tech. It's making sure that the human expertise of the bridge crew can work in perfect, seamless sync with every piece of it.
And Major, that is a point that we can never, ever forget. Despite every sensor, every satellite, and every single algorithm, the ultimate accountability for that vessel, for its crew, for its cargo, it still rests on human shoulders. The technology is an incredibly powerful tool, an amazing assistant, for sure. But it is the navigating officer's skill and the captain's judgment that has to interpret all that data, make those life-or-death decisions, and ultimately bring that ship into port safely. The buck still stops with the people standing on the bridge.
Absolutely. Okay, now let's get into the hardware that makes it all possible. What I find so fascinating here is how we basically give this giant steel structure its own senses. How does it know how fast it's moving through the water? How does it know the depth of the ocean right beneath its keel? And before we had satellites, how in the world did it know where it was in the middle of a vast ocean? These are the foundational technologies, and honestly, they are just so cool.
And it all starts with this one fundamental principle: radio wave propagation. When you strip it all down, every single radio-based navigation system, from the oldest, clunkiest direction finders to the most advanced satellite systems we have today, relies on sending a signal from one point and receiving it at another. Now, whether that signal is hugging the curve of the Earth, bouncing off the ionosphere like a skipping stone, or beaming straight down from orbit, understanding this basic process is the key to understanding how we measure time, distance, and ultimately, our position on the globe.
Okay, check this out. Let's look at one of those senses, speed. This diagram shows something called an electromagnetic, or EM log, and it is such an ingenious piece of physics. So there's a sensor on the hull, a transducer, that generates a magnetic field in the water that's flowing past the ship. Now, because seawater is conductive, as it moves through that magnetic field, it creates a tiny electrical voltage. It's simple, right? The faster the ship moves, the higher the voltage. The ship's electronics then measure that voltage and convert it into a super precise speed reading. It's literally measuring the ship's velocity by creating and reading an electrical current in the ocean itself. How amazing is that?
And the key component there, Major, is that transducer. It's a word we hear a lot, but its role is absolutely vital. You can think of it as the bridge between the digital, electronic world inside the ship and the physical world of water and sound outside. For an echo sounder, it turns an electrical pulse into a sound wave, that classic ping that travels down to the seabed. It then has to listen for the echo and convert that returning sound wave back into an electrical signal. For the EM log you just described, it's turning the ship's motion into a voltage it can measure. It's the essential translator between different forms of energy.
And this slide gives you a great look at what one of these things actually looks like. I know, it might not seem like much, but this device has to be incredibly tough. It can weigh 8 kilograms, and it's built to withstand constant pressure, the corrosion of salt water, and even impacts, all while performing these unbelievably precise measurements. It's a perfect example of the kind of rugged engineering that's required to make these sensitive electronic systems survive out there in the harsh marine environment. You're listening to OOO-TV, with research by author Paul Bullo.
So, we've got speed and we've got depth. But the biggest question in navigation has always been, where are we? For decades, this was solved with ground-based radio navigation systems. But then came a technology that completely and utterly changed the game. It moved our point of reference from towers on the coast to a constellation of satellites in orbit. This was the massive shift from powerful but limited regional beams to truly global, pinpoint precision. This here is a snapshot of the world before GPS was everywhere. On the left, you see the coverage map for a system called LORAN-C in Europe. It was an incredible system for its day, don't get me wrong. It used the time difference between radio signals from multiple ground stations to figure out a position. But you can clearly see its limits, right? The accuracy gets worse the further you get from the stations, and huge swaths of the ocean have no coverage at all. And that receiver on the right? Well, that shows the complex interface navigators had to master, manually selecting signal chains and constantly battling atmospheric interference. It was revolutionary, but it definitely had its weaknesses.
And then came this, the fundamental principle of the Global Positioning System, or GPS. And it's both beautifully simple and absolute genius. A receiver on the ship listens for signals from a bunch of different satellites. Each of those signals is precisely time-stamped. By measuring the tiny difference in time it takes for each signal to arrive, the receiver can calculate its distance from each satellite. This first measurement is called a pseudo-range because it needs a little bit of correction for clock errors to be perfect. But with signals from at least 4 satellites, it can solve for 3 dimensions: latitude, longitude, and altitude, plus that all-important 4th dimension, precise time.
But here's the thing, not all GPS fixes are created equal. The accuracy depends massively on the geometry of the satellites in the sky at any given moment. This concept is called dilution of precision, or DOP. Think of it like this. If you're trying to pinpoint a location and all your reference points are clustered together in one small part of the sky, any tiny measurement error gets magnified and your fix is kind of fuzzy. But if your reference points, the satellites, are spread out nice and wide all across the sky, your position fix becomes much more precise. This graph just shows how those DOP values change as the satellites move in their orbits. A good system is constantly picking the best satellite geometry to get the lowest DOP, and that means the highest possible accuracy. And the accuracy we can now get is it's staggering. This chart shows the horizontal error for different methods. Standard GPS, the kind in your phone, gets you down to a few meters. But with something called differential GPS, which uses a fixed ground station to broadcast error corrections, you can get that down to well under a meter. It's incredible. But Major, I have to play devil's advocate for a second here. Does this incredible, almost magical precision create its own set of problems? Does it lead to an over-reliance on a single system? We've seen accident reports where navigators get so fixated on that magenta line on the GPS display that they develop this false sense of security and lose their broader situational awareness, sometimes with truly disastrous results.
And that brings us to what might just be the most important part of this entire system. All the incredible technology we've just talked about is useless, or even worse, dangerous, if the human team on the bridge isn't functioning like a well-oiled machine. This is where the discipline of Bridge Resource Management, or BRM, comes in. It's the formal process of making sure that all the resources, both the people and the tech, are used effectively. It's all about teamwork, clear communication, and vigilant human oversight.
So here's the crucial point. Time and time again, when investigators dig into why a maritime accident happened, the root cause isn't a faulty GPS or a broken radar. The root cause is almost always a failure in communication. You see it in the reports over and over. Collisions in perfectly clear weather where one officer thought the other vessel was going to turn, but that was never clearly communicated or confirmed. Technology can't solve that problem. Only people and processes can.
I couldn't agree more, Lieutenant Cornell, and BRM gives us a clear, actionable framework to prevent those very failures. This isn't some abstract theory, it's a set of concrete practices. Things like closed-loop communication, where every single order is repeated back to confirm it was heard and understood correctly. It's about creating a culture where a junior officer feels not just able, but obligated to speak up and question a senior officer if something seems off. It's about formal briefings before entering a busy port, making sure everyone on the team has the exact same mental picture of the plan. These steps are what turn a group of individuals into a cohesive, effective, and safe team.
You're listening to OTOT TV with research by author Paul Bulow. And the evidence is just crystal clear. Despite all these amazing technological advances, these accidents still happen. And when they do, the investigation almost invariably finds that the core principles of BRM were not being followed. The team lost what's called situational awareness, that complete, holistic understanding of what the ship is doing, where it's going, and what dangers are lurking ahead. This directly links those abstract ideas of communication and teamwork to the very real-world prevention of maritime disasters.
Okay, so we've looked at the hardware, we've traced the evolution of positioning from the ground to space, and we've talked about the critical human element. So for our final section, let's bring it all together. How do we define the requirements for the ultimate navigation tool? How do we synthesize all these different elements into a clear specification for a system that is effective, safe, and truly future-proof?
Well, to build a tool like that, any proper requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation absolutely must be clearly defined in a step-by-step manner to meet three primary categories. First, you have audience needs. What does the user, the navigator, actually need to do their job well? Second, the technical requirements. What must the system be capable of from a pure hardware and software perspective? And third, you have to consider all the safety regulations and restrictions for travel. A great system has to find the perfect balance across all three of those.
Exactly. And a huge challenge here is that a one-size-fits-all solution just doesn't work. It's impossible. The requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation vary by region, size and type of vessel, and local laws and situations, weather, events, and tradition. I mean, think about it. The needs of a massive container ship squeezing through the Singapore Strait are completely different from a fishing boat in Alaska or a high-speed passenger ferry in the Baltic Sea. The system has to be incredibly adaptable and configurable. And that leads us right to this critical question, which is at the very heart of that audience needs category. How can marine navigation and piloting systems for both inshore and offshore global navigation provide a high-quality experience for the user? And the answer isn't just about cramming in more features. It's about human factors. It's about designing intuitive interfaces that actually reduce the cognitive load on the navigator. It means presenting incredibly complex data in a clear, unambiguous way. And it means providing meaningful alerts that draw attention to real dangers, not just flooding the bridge with constant beeps and alarms that lead to alarm fatigue. The goal is to make the technology a seamless extension of the navigator's own expertise.
So, Lieutenant Coronel, let's get specific. What are the key elements for the requirements specification for marine navigation and piloting tool for both inshore and offshore global navigation? Okay, on the technical side, it has to start with redundancy. You just cannot rely on GPS alone anymore. The system has to be able to seamlessly integrate data from other satellite constellations, like the Russian GLONASS or Europe's Galileo system. And real-time data integration is absolutely huge. The requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation has to incorporate existing databases of charts, maps, passages, obstacles, depths, and traffic, and it must update those maps and the planned course in real time using satellite feeds and live data from all the boat's sensors, GPS, depths, speed, current, even fuel consumption against the desired course and ETA. Exactly. Then you layer on the human factors. Things like ergonomic workstation designed to reduce fatigue on long voyages, and user-configurable displays so navigators can prioritize the information they need for the specific task at hand, whether it's open ocean cruising or delicate docking maneuvers. The system has to empower the user, not overwhelm them with data.
And this, Lieutenant Colonel, is where it gets really exciting for the future. So let's ask, can we connect to both Starlink type of satellite systems and use library data to relay time, update new geographic region, and new weather data for marine navigation and piloting tool for both inshore and offshore global navigation? And the answer is a huge, resounding yes. And it is a total game changer. Historically, updating charts was a slow, cumbersome process. But with high-bandwidth, low-latency satellite internet, a ship in the middle of the Pacific could get real-time hydrographic updates from a survey vessel that passed through that same area just an hour before. It could download dynamic, high-resolution weather models that are constantly being updated instead of relying on a forecast that's 6 hours old. This kind of connectivity is going to revolutionize the delivery of real-time data to the bridge.
And this diagram really brings our whole discussion full circle, doesn't it? It shows the sheer complexity of a modern integrated bridge system. And it proves that this is not a static field. The requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation are updated and evaluated on an ongoing basis. We have to incorporate needs and desires for new features, new benefits, and changes to existing regulations. We have to constantly bring in new technologies, new rules, and most importantly, the hard-won lessons learned from incidents at sea. The goal is a continuous cycle of improvement, creating systems that not only leverage the absolute best technology available, but that also enhance the skill, the judgment, and the safety of that indispensable human crew on the bridge.